Thanks very much for this kind recognition. So I'd like to give a quick overview of what we do in my lab at Georgia Tech in the field of vibration-based energy harvesting. Related to the theme of this conference, there's a quick, if this is going to work, a quick slide on why we care for vibration-based energy harvesting or energy harvesting research overall. Today, billions of devices are connected through the internet, and in less than a few years, by 2020, the number of devices and objects connected through the internet will exceed 50 billion. So those devices, and most of them won't even be computers, and most of them will be like functional objects, like your shoes, and or like other wearable electronics, what will be like monitoring your blood temperature, blood pressure, body temperature, and stuff like that, or in case of an emergency, transmit that information to an ambulance, and at the same time your insurance company. And so you can imagine that therefore, and there's many examples over here in this graph from Wikipedia, smart homes and stuff like that. Here's some wearable electronics. Then you can imagine that each one of us will be connected to hundreds or thousands of wireless sensor nodes, which are going to be low power nodes, but they're going to need some level of power. So the question is, how are we going to power those things? Are we going to have to charge each one of those wireless sensor nodes that are going to be connected to us in near future? Even dealing with a single smartphone and charging the battery is a burden. So that's the idea and the motivation for energy harvesting research. Might be solar, thermal gradients. In my case, it's vibration-based energy harvesting. So if you like another, like today's modern life example for complex structures like aircraft or bridges, you see over here is the Minnesota bridge from 2007 collapse. What we use in those bridges is wireless sensor networks that do structural health monitoring. Structural health monitoring is constant condition monitoring of aircraft or any kind of critical engineering application you can think of in which the failure can result in catastrophic consequences. So what happens over here in a modern bridge, as like in this example, is hundreds of wireless sensor networks communicating with each other and communicating with the technician and whoever the maintenance company is. So you don't have to do the periodic maintenance constantly. You would just know if there's something going wrong in a certain region, you just go and attend to it before any failure takes place. But then the question is, you're going to rely on either batteries or wires coming from the grid to power those sensors. Then that requires another kind of maintenance for battery replacement or checking if the wires are functioning okay. So this is another application. For instance, why not try to harvest some of the vibration in this bridge so that the monitoring can be self-powered. So hopefully I could convince that there is some merit in vibration-based energy harvesting research, and there's different ways to do that. You can make use of electromagnetic induction, or in our case, it's piezoelectric materials that we use for converting mechanical vibration into electricity. It's just a quick, again, Wikipedia kind of material over here. What it shows is mechanical deformation results in some electrical output. So this is, I'm not going to go into any materials aspects of it, but piezo in Greek means to press, to squeeze, and by deforming the structure to squeezing it, you can generate electricity, and that's the material science background of what we do. What I would like to talk about is the challenge when working in the field of vibration-based energy harvesting. The characteristics of ambient vibration is very much case dependent. So you cannot come up with with a solar panel. You can probably come up with a universal solar panel. You just try to improve the efficiency constantly. But in the case of energy harvesting, vibration spectrum, what I mean by that, I will explain in a minute, it varies. So here's one example from one project we had with, for Navy helicopters. Again, this is for structural health monitoring. You want to monitor the blades so they don't fail, but then you don't want to feed wires through the main body. This hub rotates, but there are severe vibrations over here in the hub, so you might be able to harvest part of it, convert it into electricity so that the monitoring of the blades, health monitoring, is self-powered. Then you're talking about certain frequencies. Frequency means like how many times the repetitive motion of vibration takes place in, let's say, in a second. Then when you go from an application like that to a turbofans, jet engine, noise spectrum, or walking-based energy harvesting. This is David in my lab. So some accelerometer attached on his wrist to figure out what kind of energy is available for harvesting energy for wearable electronics. So as you go from a turbine blade to the a helicopter blade to the swinging motion of an arm, the rotation, the speed is entirely different. That's why this signature of vibration is very much case dependent. This is probably the most complex slide in the sense that I have to show this because I do dynamics for a living. If you design a linear energy harvester that's going to work only for a limited frequency, that was the main contribution we did over the past years, introduce nonlinearities and complexities that otherwise you don't want to introduce in conventional systems. You don't want your building or aircraft to behave with this kind of dynamics that can undergo even chaos. But in energy harvesting, there is merit in that, so you can enhance the frequency bandwidth, so your harvester operates over a range of frequencies. Some of the prototypes that we developed and experimentally validate over the past years. As I wrap up, let me give you what the trends are these days. Multifunctionality is very important. This is a recent AFOSR project just started in last fall, in which the idea is to make use of artificially structured concepts like internal resonating components so that the main aircraft doesn't vibrate, but like these metamaterial arrangements. Meta means beyond, so it's beyond material or beyond structure. Photonics people will know it. We like to call it phononics or like acoustic locally resonant metamaterials. So you can absorb vibrations, and at the same time, why not absorb structural vibrations and convert it into, again, electricity so that you can power a sensor network. Then things get more complicated if you're propagating waves. Why not try to localize the energy either using mirror or lens concepts? So one last slide. First, I'm going to skip this wireless power transfer. In some cases, by the way, you still have electronic nodes, but you don't have ambient vibrations. Then in that case, you can transfer power from one domain to the other through sound waves, like ultrasound waves. And finally, we are looking at also in a new NSF project on harvesting at nanoscale. What if you have nanosensors, or you don't want to come up with, like nano means, by the way, a thickness level 10,000 times thinner than your hair. So what if you have nanosensors? You don't want to come up with like a centimeter scale energy harvester to go with, like, to power a nanosensor. And we are looking at polarization dynamics at that scale. Even non-piezo materials can give you electrical output due to gradient effects. Thanks so very much.